Hello everyone, and welcome back to the CIV 398 Assignment 2 Guide. So in this video, we're going to be covering question number 2, which is very similar to question number 1, except we're going to look at one of the oddities, if you will, of finding eigenvalues and eigenvectors. So the question itself says, considering the following matrices, and we have two matrices, they're both 3 by 3, and they're labeled A and B. And it says, determine the eigenvalues and eigenvectors of each matrix, and then it says, which matrix has imaginary eigenvalues? Or if you guys remember, imaginary numbers is basically the square root of -1. If you square root a negative number, it technically doesn't exist, which is why we call it imaginary. And what we're going to find out is that one of these matrices, either A or B, has imaginary eigenvalues. And part C asks us, comment a reason why one of these matrices has imaginary eigenvalues. So if we look at the matrices really quick, again, they're going to be random numbers, so everyone's going to have different ones. But what you guys should see is the only difference between these matrices is the sign of that number. So matrix A, it's a positive sign, and matrix B, it's a negative sign. So that's the only thing that should really change between your matrices. However, it'll lead to big changes when it comes to the eigenvalues and eigenvectors. So much like before in question 1, to determine eigenvalues, which we're going to denote as lambda, we need to solve the equation the determinant of m minus lambda I is equal to 0. And before we had a 2 by 2 matrix, so it wasn't that bad to do by hand, but now we have a 3 by 3 matrix. So again, I'm going to say option 1 and option 2 because by all means, you guys can go into Mathematica and solve this, of course, and I'll give you guys kind of the function you need to do it afterwards. But in order to really understand where these imaginary eigenvalues come from, I'm going to show you guys the solution by hand. And the solution by hand will really emphasize where these come from. So let's say we have our matrix M, and the first row is A1, A2, A3, the second row B1, B2, B3, and finally the third row is C1, C2, C3. Well, just like before, I can go the determinant of m minus lambda I is equal to blah, 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 which is equal to 0. So the first step is we need to expand that out. So if I expand this out in its current state, we're all thinking the same thing. It's absolutely disgusting. No one wants to touch this. No one wants to factor this. Even though technically our only unknown is lambda, it's still a mess because there's so many different parameters going on. Luckily for us, the problem definition has some simplification because it says that B1 is equal to C1, which is equal to A2 and A3, which is 0. So if I were to look at M now, except substituting those zeros where I have them, well, then my new determinant actually becomes much more manageable. So again, our only unknown here is going to be that lambda, because A1, B2, C3, we all know we know them, as well as B3 and C2, of course. So if you guys were like me in math class, the first thing I do when I see something like this, even though it shouldn't be a good way to do it, is I would factor it into one nice equation. In this case, it'd be a cubic equation, and then I would try and solve for the roots, which, let's be honest, I'd use Wolfram alpha or something like that. However, that won't be of much value in this course. So we're going to have to try and think of a smarter solution in order to solve these roots. So what I like to do for the determinant case, it'll always be very, very nice in that we can have a linear and a quadratic equation. I know you guys are saying, okay, well, Clayton, what exactly do you mean by that? Well, I mean, we literally have a linear part with A1 minus lambda. And then what I did is I took everything inside those square brackets and converted that into a quadratic equation of irregular form. So again, I took the A1 minus lambda and I said, okay, well, that's already a root. Why would I change that? Why would I try and factor that in? That's a nice linear root. I'm just going to leave that be. And then what I did is I took everything inside that square bracket and I factored it into a nice quadratic equation in the terms of ax squared plus bx plus c is equal to 0. So we know for quadratic equations, they have two roots. So if I were to go and say, okay, well, let's look at the linear equation. A1 minus lambda is equal to 0. Well, it's easy to conclude that lambda 1 is equal to A1. That's just trivial at this point. You guys are laughing. But now we look at the quadratic equation. I say, okay, well, if we have it in the standard quadratic form, we can use the quadratic formula. So therefore, lambda 2, 3 is equal to this equation. So the difference between lambda 2 and lambda 3 is the plus or minus just before the square root sign. And the reason why I wanted to highlight this is because in this quadratic equation, we have a square root sign. And as I told you guys, to get an imaginary number, we need a negative inside of the square root. So if we were to look at this square root right here, if we have a negative value, so negative b2 minus c3 squared minus 4 times b2 c3 minus b3 c2. Well, that was a mouthful to say. If that term altogether is negative, then that's what will result in the imaginary eigenvalues. However, this is messy. 3x3 matrices, they become a lot of work, computationally pretty heavy. It's doable. I know you guys can do it, but why do all that work when you guys can do Mathematica? So the Mathematica code is very similar to that of question 1, where all we need to do is add that third row of C1, C2, and C3. So we have a third subset of squiggle brackets, but the command to find the eigenvalues is still the same. So all we have to do is add on to our matrix M, and then all we have to do is go eigenvalues of M. So again, remember the capital E as well as the square brackets around the M. Press Shift and Enter, you're good to go. And the eigenvectors, well, it's also the same procedure as that as question 1. So to determine the eigenvectors, which we're going to say P, we need to solve the equation MP is equal to lambda P. So we have the option to solve it by hand, so we can expand everything out. We have our nice matrix times the vector P is equal to lambda times the vector P. And again, we know everything in that matrix M, so all the A values, the B values, and the C values we know. Lambda we also know. So our only unknown right here is P1, P2, and P3. And this creates 3 equations. You guys are thinking, oh great, we got 3 equations, 3 unknowns. We can solve for P1, P2, and P3. However, just like the case in question 1, we're going to find that there's infinite solutions. So in order to solve this efficiently, what we do is we assume a value for P3, which I assume is always 1. So I assume P3 is equal to 1. And then from there, I can take the first 2 equations and solve them. So now I got 2 equations with 2 unknowns, P1 and P2. And after I find P1 and P2, I have my first eigenvector. So remember, this is the eigenvector corresponding to whatever lambda I used in that equation. Now, since we have 3 different eigenvectors in this case, we're going to have to go through and find the eigenvectors for each eigenvalue. However, oh, and I should probably note that, again, this is not normalized. I always need to add that because a lot of students will usually quit here. But most of the times in an exam situation per se, we want normalized eigenvectors because, again, there's infinite cases. So we usually go with the normalized one. That's kind of the standard. Yeah, not too much fun, just an extra step, but I know you guys can do it. Because what we're going to do next is saying, okay, well, solving by hand, that's great, but I don't want to do that. I'm too lazy. Well, we do have the option in Mathematica. So by this point, we should already have our matrix M defined. It's the same thing we used for the eigenvalues. And all we have to do is switch eigenvalues function to the eigenvectors function. So I type in the eigenvectors of M, go Shift and Enter, and I'll have my eigenvectors of M. So at this point, you guys have basically done the hard work of the question, finding the eigenvalues and the eigenvectors of the 2 matrices. And again, one of them will be, of course, imaginary. So all you're going to have to do is comment which matrix is imaginary, and then you're going to try and comment why. So when I showed you by hand, I kind of showed you what has to happen in order for them to be imaginary, but kind of the trick to this question is, and I know this is a new topic that we're only recently covering, is look at the symmetry of the matrix. As you guys will see, one of those matrices is symmetric and the other one is not symmetric. And kind of the little tip is, if a matrix is symmetric, it will always 100% of the time have real eigenvalues. Now, if it's not symmetric, that doesn't mean it's always going to be imaginary eigenvalues. It just means it's possible. So we can have a symmetric matrix with real eigenvalues. Or sorry, we can have a asymmetric matrix with real eigenvalues, but we can also have an asymmetric matrix with imaginary eigenvalues. So if it's asymmetric, it goes either way, but if it's symmetric, it'll always be real. So in essence, that concludes question number 2. Again, if you guys are using Mathematica, it'll be a breeze for you guys, but just pay attention to where the imaginary eigenvalues come in, because that'll play a big role when we see the bonus question. So thank you guys so much for listening. I hope this helped. If not, then I'm sorry. I'll try and do better next video. But yep, again, thank you guys for listening. I will see you guys in question number 3.